Hello dear students, welcome back to the lecture series on theory of semigroups with course code MMTE 405. Today in this lecture we are going to prove Green's theorem. So let me first recall the lemma which we have done in previous lecture and states that if A and B are D-related, if A is D-related to B, then there is a bijection from H class of A to H class of B. That means their coordinality is same. There is a bijection at that time if A and B are D related. So it means that so therefore from this lemma we deduce that if A and B are R related, so that means they are also D related, then there is a bijection from HA to HB if they are R related, because whenever they are R related then they are also D related. So whenever they are D related then there is a bijection from HA to HB. So this is true. So therefore if we have if AS is R related to B, if AS is R related to B, then this mapping, which is the right translation, which maps X on to XS, is bijection. Is bijection from HAS or HA. It's actually AS to A. Sorry, AS is R related to A. Then there is a bijection from HA onto HAS, or we can say the cardinality of HA is same as cardinality of HAS, H class of AS. It follows from this lemma. So if AS is R related to A, then there is a bijection which we define by this rho S of X equal to XS, and when we restrict that bijection to HA, it will give the, when we restrict that map to HA, it will give the bijection from H class of A onto H class of AS. So in other words, the cardinality of HA is same as cardinality of HAS. So this also gives the following: if AS is it means that if AS is H related to A, suppose they are H related now, then again if they are H related, then they are also R related, because H is subset of R, H is the intersection of L and R. So it means that whenever AS is H related to A, it means that AS is R related to A, and whenever AS is R related to A, then there is a bijection from HA onto HAS. But since HAS is H related to A, therefore HA is same as HAS. So in other words, we can say there is a bijection from HA onto itself. Onto itself means onto HA, because at that time this HAS will be same as HA, as they are H related. AS is H related to A, so therefore their H classes must be equal. Their H class must be equal. So it which is this AS. If AS is H related to A, then there is a bijection from HA onto itself. So now we have a following lemma, and it's also, so we have also the dual of this, dual argument of this. So which we at that time we are using the left that lambda, and also we have a left translation mappings which maps X onto Sx. So let me first state that lemma, which includes both the statements. So let me write this lemma here. This lemma is let X and Y, let X comma Y, they are elements of S, the elements of S as a semigroup. If xy belongs to X class of H, so in other words, xy is H related. Sorry, xy is H related to X. This. Then the map which is rho y, which is a map from when we restrict it to Hx, it will be a bijection. Is a bijection of Hx onto Hxy actually, but Hxy is same as Hx onto itself. I can see onto itself. So this map rho y, if this map rho y, which is a map from actually S to S, rho y of x equal to xy, that's this map rho y of x equal to xy, right translation, it's a map from S to S, but when we restricted this map to Hx, it will be a bijection from Hx onto Hx itself. Okay, and its dual argument is if xy belongs to Hx, hy now, not Hx, hy. So in other words, we can say xy is H related to y. It's H, that means their H classes are same. Then this right translation, which is lambda x, when we restrict it onto hy, so lambda x of y equal to xy. Okay, lambda x of y equal to xy. That's this map is bijection. Is a bijection. Is a bijection of hy onto itself. So both these statements, they follow from the previous discussion where we have seen that if AS is H related to A, then there is a bijection from HA onto itself. HA onto itself. Okay. And similarly, if this AS is related, H related to A, then there is a bijection. Let me write here SA. No. SA is H related to A, then there is a bijection from HA onto itself again. So it follows from our previous discussion. We have already done this. So this lemma follows trivially, or you can say it follows from the lemma which we had done in the previous lecture. Okay. So those mappings, those translations, this is right translation, this one is the left translation. They are when they restricted onto Hx and Hy respectively, they are the bijective mappings onto the set itself. Onto the set itself. Now next we have a theorem that we call the Green's theorem. Green's theorem. Okay. Green's theorem. So the statement is if H is an H class, if H is an H class, so it is an equivalence class with respect to the equivalence relation H. It's an H class in a semigroup S. In a semigroup S, okay, then either H square means H into H, the limits of H square are the products of elements of H with itself. Okay, then either H square intersection H, it's either null set, it's an empty set, or if it's not empty, if it's not empty, then they're equal, or h square is equal to h, and h is a subgroup, and h is a, this is a very important theorem, it's a subgroup of S. So these H classes, they are either subgroups. If they are not subgroups, then the intersection with H square with H is the empty set. Okay. Let's prove this theorem. Very simple, not too difficult. So if the intersection is the empty set, then there is nothing to prove. Then there is nothing to prove. Then there is nothing to prove. Okay? Now suppose the intersection is not equal to phi, it's non-empty. Then I can find A and B such that A into B belongs to H. Because this set is non-empty, so let me explain it. So let's suppose that X belongs to H square intersection H. So that means X belongs to H square. So which implies there exists two elements A and B in H such that X is equal to AB belongs to H. So this is the case. Okay. Now you can see that this AB, it belongs to H by previous lemma. Where we have seen that whenever xy belongs to some H class, say H class of X, whenever xy belongs to H class of X, or xy belongs to H class of Y, then in that case there is a bijection which will denote by rho y from Hx on to Hx. This is a bijection. And in the second case, if this is the case, then there is a bijection which I denote by lambda x, which is a bijection from H class of Y onto itself. This is from the previous lemma. Now look at here. Since A belongs to H, so A belongs to H means that since A belongs to H, it implies that H is equal to H class of A actually. It's equal to H class of A. Because A is in H, so H class of A is equal to H. Okay. Now look at this here. Since AB belongs, so that means AB belongs to HA, and also this B belongs to H. So this implies H is equal to HA is equal to HB. So AB belongs to HA, which is equal to HB. Now you can apply the previous lemma. So which states that there is a bijection which is rho B here from then there is a bijection rho B and lambda A from rho B is from HA onto itself, and lambda A is from HB onto itself. There are two bijections. One is from HA onto itself and second is from HB onto itself respectively. These are two bijections. So this now look at this one bijection rho B, which is the bijection from HA onto itself. That's actually H to H, which is defined by rho B of H is equal to BH. So in other words, we can see that this it's a right translation actually. It's here HB. HB. So we can say that HB B is H. This means HB belongs to H for all H in H, because it's a map from H to itself, and image of H under row B is HB, right translation. So that element belongs to H. And similarly, this map row lambda A, which is actually the right translation, and from this you can conclude that AH belongs to H for all H belongs to H. Now we have this HP belongs to H, which is equal to HA equal to HB, and AH belongs to H, which is equal to HA equal to HB. Then we can again apply the lemma, previous lemma, and we can see that this one you can again by previous lemma we can see that HA is equal to by previous lemma. You can see this H is equal to H is equal to H for all, this H for all H in H. It follows from previous lemma. Okay, H belongs to H for all H belongs to H. So how can we obtain this one? It's very simple. Let's take an element here. So to prove it, H is equal to H. Now, if I take any element here that X belongs to H, this implies what's XH actually? It's the right translation. It's actually rho H of X. But rho H of X, you can see here, rho H of X. It's actually right translation here. Rho H of X. So it's the right translation, and rho H of X, which is equal to XH, and it's a map from H onto H itself belongs to H. Okay, rho H of X is equal to XH, and this is here. You can apply it here. AH belongs to H. So that means rho H of X equal to X. Actually, from this one it conclude from this equation. Rho H is a map from H onto itself, defined by rho H of X equal to XH. It's true for each X belongs to H. XH belongs to H. So X H it belongs to H, but what's XH actually? XH belongs to H, but XH is an element of this one. So this implies H is subset of HH. H is subset of HH. And conversely, if I choose any element here, X, then X times H, it belongs to by the same argument. By the same argument. And if X comma H belongs to HH, then you can see this. Then this X belongs to H, which implies what's XH is equal to rho H of X, that also belongs to H, which implies this HH is subset of H. So therefore, H is equal to HH. And similarly, you can see that similarly. HH is equal to H. So that means it's a semigroup H. Also, we need to show that now this H is actually a semigroup. That's again simple, because H square is equal to H. So also H square is equal to H, because any element of H is a product of two elements of H. H square is equal to H. So that means therefore H is a semigroup. H is a semigroup. such that HH is equal to H for all H belongs to H. So in other words, for all AB belongs to H, AX equal to B and Y equal to B have a solution in H. Because of this, HH is equal to HH is equal to H. So thus H is a subgroup of the semigroup S. So this proves the Green's lemma. This proves lemma, which you call Green's theorem. Sorry, which you call the Green's theorem. So next, which also it follows from this theorem. Next theorem, which states that if E is an idempotent, then in a semigroup S, if is an idempotent in a semigroup S, then E class of H is a subgroup of S. E class of H is a subgroup of S. And one more thing, no H class contains in S can contain more than one idempotent. No H class can contain more than one idempotent. So if H is any H class of a semigroup S, either this H does not contain any idempotent, or if it contains an idempotent, then it contains only one idempotent. Okay? So let me prove this theorem, which is again simple. Now you can see this. We have a proof. We have this E idempotent. It belongs to the H class of E. It's an equivalence class of E. It contains E at least. So, but E square is equal to E. It also belongs to H square. Let me denote this by H. So that means H intersection H square is not equal to 5. It's non-empty. Because H square contains E, because E is same as E square and E square belongs to H square. So this intersection is non-empty. So whenever the intersection is non-empty, then therefore by previous theorem, by Green's theorem,